Hi everybody, this is Mechanical Engineering by Hand, and in this video I want to talk about pipe head loss with a gas. This is the Darcy-Weisbach equation, which can be used with liquids and gas. When it's used on a gas, if the change in pressure is less than 10%, you just use the supply pressure. But if the change in pressure is between 10 and 40%, then you want to recalculate using the average pressure. And technically this would be a compressible flow problem, but you can get a satisfactory answer with this method. Okay, so I have this example with compressed air moving through a pipe, and there's a device at the end demanding 100 SCFM. So I've got atmospheric pressure at 15 psia, just to simplify things, and then 68 degree air at 120 psi moving through this pipe. And it's a 1-inch Schedule 40 pipe. The ID is 0.0874 feet. The area is 0.006 feet squared. The specific roughness is 0.0002 feet. E over D is 0.0023. And the length of the pipe is 1,000 feet, and there's 50 elbows and 10 T's where the air is flowing through and not through the branch of the T. Okay, so converting those fittings to an equivalent length, the elbows are 5.2 feet each, and we have 50, so that would be 260 feet. The T's are 3.2 feet each, and 10 of them, so 32 feet. And then we just add those, the 1,000 feet plus 260 plus 32 is an equivalent length of 1,292 feet. And the absolute viscosity of air, which is independent of pressure, so you only need to look at the right temperature. So for 68 degrees Fahrenheit, the absolute viscosity is 3.75 times 10 to the negative 7. And then the specific weight is the standard weight of air times the pressure ratio. So we have 0.6 pounds per cubic foot, and then the density of that air would be the 0.6 divided by gravity, so 0.0186 slugs per cubic foot. And then the kinematic viscosity, which we'll use to calculate the Reynolds number, is the absolute viscosity divided by the density, and so that is 2.02 times 10 to the negative 5. Okay, so I did that to kind of speed things up, but let's start with the first guess. And what I'm going to assume is that there is no pressure loss, and so our pressure through the whole pipe is 120 psi. So let's start with that. Assume change in pressure equals 0, and so our average pressure equals 120 psia. Converting the 100 SCFM to ACFM, times 15 over 120 equals 12.5 ACFM. And then our velocity is cubic feet per second over area. So that is 12.5 divided by 60 divided by the area, and that is 34.7 feet per second. And then Reynolds number, diameter times velocity over kinematic viscosity, and that equals 150,000. And then when I look this up on a Moody chart, the friction factor equals 0.027. Okay, so now we have everything to calculate the head loss. So that head loss in feet is 0.027 times 1292 times 34.7 squared over 2g is 64.4, and the diameter 0.0874, and that equals 7,463 feet. Okay, now we need to convert that to PSF and PSI. So PSF is just the feet, 7463, times our specific weight of 0.6, so times 0.6, and that is 4478 PSF, which is equal to 31 PSI. Okay, so in this assumption, P1 equals 120, and then P2 is that minus our pressure loss, so 89, and our change in pressure is 26%. So we're in this category where we need to recalculate using the average pressure. So let's do that over here. Let's calculate the average pressure. It's just going to be 120 plus 89 over 2, which is 105. So over on this next iteration, we'll use P average equals 105. And we need to find the ACFM again, 100 SCFM times 15 over 105 this time is 14.3 ACFM. And then our velocity, 14.3 over 60 divided by 0.006. I'm using the CFS over the area. And that equals 39.7. Okay, and then our specific weight is 0.075 times 105 over 15. And that is 0.525 pounds per cubic foot. And then kinematic viscosity equals absolute times gravity over the specific weight. And so that is 2.3 times 10 to the negative 5. Okay, so Reynolds number is dV over V using the new velocity and kinematic viscosity, and that's 151 K, so it's about the same as our first guess. So I'm just going to say that the F hasn't changed, so 0.027 again. Okay, now we can calculate this head loss, and so it'll be 0.027 times 1292 times 39.7 squared over 64.4, and the diameter 0.0874, which is equal to 9768 feet. Okay, so we need to find the PSF again. PSF equals 9768 times our specific weight, 0.525, and that is 5128 PSF, and that equals 35.6 PSI. Okay, So on this guess, P1 is still 120 PSIA, and P2 is 84.4 PSIA. So this now this pipe, if this were installed in a plant, it would be way too much pressure loss. You'd probably want to go with 5% or less. The only time I can think of a pressure loss being this high would be like an overland transport pipe, but that's not going to be made of 1-inch pipe. It's going to be much bigger. So I'm just using this example to show you how this works, but if this were being installed in a plant, I would definitely upsize this pipe to where you have say a 5% loss, which would be like about 6 psi at the end. So another way to do that is to look on a pressure drop chart for compressed air, and I have one in this book by Spirax-Sarco. They deal with steam, but for some reason they have this chart in their book. And on this table, it shows you the pressure loss, and they're kind of showing you how to do it. You have to start with your SCFM, find out where it meets your PSIG, and then you follow these diagonal lines down to your pipe size, and then go down to see what the pressure loss is. So in our case, I have these green markers on here to help me out. We started with 100 SCFM, and they're calling that free air, so they're talking about unpressurized air, and we had 100. So we go over to 105 PSIG. They have this scale and gauge pressure here, so 105 would be right about there, and then we follow this diagonal line down to the 1-inch pipe, and you can see where kind of I got lucky. I didn't plan this out, but it just happened to be sort of on the scale. It's in the box, but there's no numbers down here, so that's a good indicator that your design, there may be something wrong with it if you're off charts like this. But anyway, that would end up here, which is about 2.4, and that's per 100 feet. So when you multiply 2.4 times this 1292 and divide that by 100, you get 31 psi, which is interesting because it's what we got for this first iteration. So I think this chart is good. It's just assuming that there's really no effects from the compressible flow. So if we were actually doing this in real life, I would go with this pressure drop, which is a little bit higher than the 31. All right, I hope that was helpful. Thank you for watching.